So before we get to practice what we're doing today, which is on limits, something you've never done before, I just want to introduce uh, a quick little scenario that might connect us to calculus and to Isaac Newton. And if you watched the video before this, you recognize in terms of where we get calculus, in terms of the Greeks, Isaac Newton, Leibniz, and so on. It's a brand new branch of mathematics. And why do we need that branch? We talked about it. Professor Dave talked about it in the last video. But I just want to do a simple scenario for you so maybe you can help understand the idea of a limit and why we have that limit. So here's a table of values. You do not need to write this down. It'd be great if you just listen. So here's a table of values. And I want you to think of this scenario that you're driving to Santa Barbara. And from here to Santa Barbara, let's say the distance there is 180 miles. And so you get into your car, van, truck, and you drive to Santa Barbara. You don't take any breaks. You are driving the entire time, no breaks. After the first hour, you've covered 50 miles. After the second hour, 2 hours in, 110 miles, and then finally get to Santa Barbara, that's 180 miles, and it took 3 hours to get there. If I asked you, what average speed were you going? How would you find average speed? Well, I wonder if you remember this basic formula. And the formula is distance is equal to rate times time. And sometimes we say the word dirt to remind us of that relationship. Distance is equal to rate times time. So when I'm talking about average speed, that's rate. So if I wanted to get the rate by itself, I would divide by time. So it would be distance divided by time. So in the first hour, how many miles did you go? 50. And what time did it take to get there? 1. So you just go 50 over 1. It would be 50 miles per hour. Simple. How about after 2 hours? What would it be? Well, it's 110 miles. That's the distance. For 2, so you go 110 divided by 2. That's 55. Now your average speed is 55 miles per hour. And then for the whole trip, the distance divided by the time it took, 180 divided by 3, and you get 60 miles per hour. Now, when I find that, that doesn't mean you're going 60 miles per hour the whole time. That means sometimes you might be stuck in traffic. Sometimes you might be going like 75 miles per hour. Sometimes you might be going 40 miles per hour. It changes consistently. But on average, over the whole trip, it took 180 miles, and the time it took was 3 hours. Simple, right? That is basic algebra. Where does calculus come in? Well, calculus comes in understanding this. At exactly 1 hour and 5 minutes into the trip, how fast are you going? So this is the key word, at exactly 1 hour and 5 minutes. Exactly, how fast are you going? Now remember, you haven't stopped. You are driving the whole way there. So if you're driving the whole way there, we call that continuous the whole way there. We have a table of values that just shows some values along the trip. But what happens when it's exactly there? So let's look back at this again, and then we're going to define it. So in this situation, in terms of distance divided by time, exactly at 1 hour and 5 minutes. Well, we have not covered any distance at exactly that time. So 0 amount of distance has been covered. And the time at exactly 1 hour and 5 minutes, again, no time has been covered because it's exactly at 1 hour and 5 minutes. We call this instantaneous. So how do I figure it out? I know I'm traveling at a certain speed, but I don't know how to find it because I need a change, and that symbol means change. I need a change in distance, and I need a change in time. But in this scenario, at exactly 1 hour and 5 minutes, there is no change in distance and there is no change in time because it's instantaneously at that moment. So I know there's an instant, and we're going to use the word velocity coming up soon enough, but we know there's something that's instantaneous, but we don't know what it is. So we have no change in distance, no change in time. There's a special word we use for this, and that is not undefined, but it's indeterminate. Meaning we don't know. What's 0 divided by 0? We don't know. It's nothing divided by nothing. There's no way to answer that. There could be something or it could be not. Now, what does a limit do to help us in this situation? Well, a limit says this, that if we could find at 1 hour and 4 minutes and 59 seconds. How fast were you going between that and 1 hour, 5 minutes, and 1 second? Now, 1 hour, 4 minutes, and 59 seconds, 1 hour, 5 minutes, and 1 second. If I can see that now we have a time change and a distance. So we actually have something to calculate in terms of those two things. Now, the answer you come up with may not exactly match, but it'll be close enough. Now, what is it exactly when it gets there? Well, if these two numbers match, so the number on the left and the number on the right, then we can get the answer to this, even though instantaneously it was 0 divided by 0, which is indeterminate. So that's what a limit does. And we use the word approaching. So as it approaches, now this is before, as it approaches, and this is after. What are the answers before and after? So as it's approaching, can we say what the answer is that way? And we're going to get smaller and smaller and smaller and smaller and smaller until we have an answer right there. That is a limit. That is what Isaac Newton had to discover and be able to figure out for calculus. This idea of instantaneous rate of change. So we're going to work right now on limits to be able to understand what Isaac Newton was discovering in mathematics. So let's talk about limits and end behavior, and then think about that scenario of instantaneous rate of change and how mathematically we can get there, even though we have that situation of 0 divided by 0, which is indeterminate. Okay, so here is a graph, and what we're going to do together is we're going to be able to understand the end behavior of this, but instead of writing down the right end or the left end, we're going to write it in terms of what's called a limit. So I want you to look at it. Tell me this end and this end. So what we did before when we talked about end behavior, this is what we wrote down. We said as x approaches infinity, the function approaches, and then the right end goes to negative infinity. And then we did the same thing on the other side. As x approaches negative infinity, the function approaches positive infinity. And we wrote it in that notation. And we had the concept of approaching, but not the concept of a limit. All right, let's look at the second one together. So again, in Math 3, or in compacted math, we talked about the end behavior in this way, with this notation. So for the right side, we said as x approaches infinity, and then the y-coordinate, the function, what's the y-coordinate? Well, this is not going up or down, it's approaching an actual number there. So the function's actually approaching 1. That's a horizontal asymptote. And as x approaches negative infinity, the same thing's happening on the left side. It's also approaching 1. Now 1 is approaching 1 from underneath, 1 is approaching 1 from on top, but they are both approaching the same answer on the right side and left side. This is the notation we used in first semester. So we're going to take that concept, and instead of writing it this way, we're going to write it as a limit. So what is a limit? It's the concept of a function approaching a certain value. And really, in most graphs, it's the y-coordinate. So the concept of a function approaching a certain value, usually the y-coordinate it's approaching, and it's called a limit. So what does the notation of a limit look like? Here's your first introduction to something brand new. So instead of using the word limit, we use the shorter form of that, which is LIM. But that still means limit. And underneath that, we're going to say as x approaches. Now, whatever that value is, we'll just call it c. It could be infinity or any other number. It could be anything. And then the function we're using will be right there beside the limit. So limit on top, x approaches something on the bottom. That's part of it. Beside it, f at x. And then we're going to have an equal sign. And then that L is really going to be the y-coordinate it's approaching. So we're going to practice that notation so you get comfortable with something that you've never done before. Kind of what we did for logarithms or other things, trigonometry, new notation, new vocabulary, but we're going to learn it together. So we're going to write this as a limit. So how do I write the left end as a limit, and how do I write the right end as a limit? So I'm going to just write down left end and right end, and then I'm going to write it as a limit. So here we go. We're going to write down limit as x approaches. Now, the left end is when it approaches negative infinity. We have a function, so we're just going to call it f at x. And then what's the answer? Where's the left end going? And the left end is going to negative infinity. For the right end, we're going to do the same thing, limit. Now, for this situation, for the right end, we're going to say as x approaches infinity, again, we have a function f at x. And then where's the right end going? It is also going down, so that in math, we say that's going to negative infinity. Done. So we're going to practice this notation with the end behavior. So left end and right end. So let's start here. Limit as x approaches negative infinity of f at x equals. Where's the left end going? To negative infinity. We're going to write down the limit as x approaches infinity of f at x equals. And where's the right end going? To infinity. So it's a shorter, more compact way to write down end behavior. And knowing that infinity is something we can only approach. So that's why it's really important to use the concept of a limit, that it's approaching and something that is not equal to often. That's that arrow. Number 5. Let's see if I can make sure it's nice and compact here. So the left end behavior of f at x. So the left end is going up, so it's going to infinity. And then again, we're going to write it as a limit. The limit is x approaches infinity, f at x. And again, the right end is going up. Let's look at number 6. And it's just practicing the notation. So where is the left end going? Now make sure you got the left end right there. So I know it doesn't look it necessarily, but it is going down forever there, the left end. I'll circle it. And then to write down the limit as x approaches positive infinity, that's the right end behavior. And we're just practicing a new notation. Limit, x approaches something, f at x, it's all beside each other, then equals, and then the answer. And the right end is going up, even though it looks like it's going up slowly. Again, the right end, left end. Let's try it. Limit as x approaches negative infinity. That's left end. Of what? Of f at x. Write it down. Equals. Well, where is the left end going? It's going up, so it's going to infinity. Let's look at the other end. This one's going to be a little different. So the limit as x approaches infinity of f at x equals. So where's the right end in this case? Well, the right end flattens out to a number, 1, 2, 3, 4. So it's getting closer and closer to -4. So the right end is going to -4, the left end is going up. This is an exponential function compared to a rational function or a parabola, and so on. Here's another rational function. 8. Where's the ends going? So let's write it down first. The limit as x approaches negative infinity of what? Of f at x equals. So where's the left end getting closer to? 0. How about the other end? The limit as x approaches positive infinity of f at x. Where's the right end going? Also to 0. All right, turn the page. Now, what if c is a certain value? Then the limit is the value in which x is approaching from either side of c. It's important to understand that a limit is not what happens at c, rather what is happening to the function near or close or as it's approaching. So here's an example. What's the limit as x approaches 2 of this function? By completing the table of values and then verify with the graph. So let's fill this out, and we're going to use Desmos to fill this out. You can see there's your assignment ready to go almost. So I'm going to go to Desmos. Can you go to Desmos? Oh no. You can't see Desmos because I didn't put it on for you to see Desmos. All right, I'm going to do part 2. So this is part 1, and I'm going to do another video that starts here with part 2.